Hi, in the last video, mm, you saw this periodic table portion with scores of the atoms in terms of how strongly they attract the electrons in a chemical bond. That strength is called electronegativity. You saw me use the electronegativity scores to figure out if the bond was polar or nonpolar. Here it is. Here I figured out using subtraction if the bond was polar, meaning the difference is more than 0.5, or nonpolar, meaning the difference was less than 0.5. And then you saw me draw an arrow symbol for the 3D sketch, like this, where I pointed the arrow at the um, atom that was more electronegative. It had the higher electronegativity score. I did that for all of the bonds that were polar, and I did not do that for any of the bonds that were nonpolar. There is another question on your lab report document which is important for your understanding of the way chemicals behave. And that question is this: the molecular polarity. Is the molecule polar or nonpolar? This will allow you to determine if the molecule will do the intermolecular forces of dipole-dipole forces or the intermolecular forces of the van der Waals forces. You remember there were three intermolecular forces that I showed you in class: the hydrogen bonds, dipole-dipole forces, and van der Waals forces. Nonpolar molecules do the van der Waals forces. Polar molecules do the dipole-dipole forces or the hydrogen bonding. Now, it is necessary to know which bonds are polar when you determine if the molecule is polar or nonpolar. But it is also necessary to know the shape of the molecule, and here's why. I already have a page actually for you here. Okay, so here's why. Okay, so here's why. Suppose you have this molecule, CCl4. I'll draw this in black. I will draw the Lewis structure now. Cl, 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 Cl. You could tell already that there are four polar bonds here. This bond is polar, this bond is polar, this bond is polar, and this bond, all these bonds are polar, okay? So should the molecule be polar? No, this molecule should not be polar because I know the shape of the molecule and I know that all of these arrows will cancel each other out. Here's what I mean by that. There's an arrow pointing this way and an equal arrow pointing this way. The difference here is 3.5 minus 2.5. So the difference for this bond is 1. The difference here is also 3.5 minus 2.5. So the difference in electronegativity is 1. So what does that mean? The value of this arrow is 1. The value of this arrow is also 1. So this arrow and this arrow, because they point in opposite directions, will cancel each other out. This arrow and this arrow also, they're pointing in opposite directions, so they will cancel each other out. The net effect is that this whole molecule is nonpolar. Nonpolar. Did you see that? All of the bonds are polar, but the molecule is nonpolar. All right. Now, I just did that on this flat screen, as though it were done on flat paper. That is just to help you to understand the thinking that goes behind deciding whether this is polar or nonpolar. You can't make that decision on flat paper the way I just did. Why? Because the molecule is not flat. You have to know the 3D shape of the molecule. In the lecture 1.5 weeks ago, I showed you how to use a table like this from your textbook. This is page 118 of your textbook. I showed you how to use this table to determine the molecular shape. Now, the molecular shape of this molecule is like this. Let's see. Not like that. It is, no, not like that, sorry. It is this, yes. This is CCl4. The center atom is C, and these green atoms are Cl. This is CCl4. You see, if I were to stop spinning this thing for a minute, it is not looking like a plus sign. I mean, if you looked at it like this, then you might dare to say that no, actually, there is no way to make this look like a plus. Okay, if you look at it like this, you might dare to say it looks like a plus sign, the way it looks in the flat picture. But the fact is that this thing is, this CCl4 is 3D. It is still true, however, that all of the dipoles, all of the arrows that you would draw, cancel each other out. And the reason is all of these bonds are the same angle from each other. These bonds are all evenly spaced out throughout the molecule. So if this one is pointing in this way, there are 3 others pointing in the other way, and they will together cancel this one out. Notice that they are not pointing exactly in the other way, but there are 3 of them, so they will cancel this one out. What about the other one? Like this one up here. This one is pointing this way. There is nothing pointing exactly the opposite way. However, there are 3 others pointing almost, they're partially pointing in the opposite direction as this one. So they will cancel that one out. That will happen to all of these bonds. All of the dipoles here are canceled out. By dipoles, I mean the arrows. All of the arrows here are canceled out, just like they are on the flat drawing, the Lewis diagram. Okay, so that molecule is nonpolar. This molecule is nonpolar. If the geometry is evenly spaced out, it's going to be nonpolar. Here, let me give you another example. What about this one? Do you remember this one from the first video? Is this going to be polar or nonpolar? If you look at this model, you're going to make this with an actual toy. But here, I'm just showing you with software the 3D structure. Is this going to be polar or nonpolar? Well, we know that the chlorine-carbon bond is polar because chlorine has a higher electronegativity than carbon. So there will be a dipole arrow pointing to the chlorine. There will be a dipole arrow pointing to this chlorine also. But these carbon-hydrogen bonds do not get dipole arrows because their electronegativity difference is less than 0.5. Remember, it was 0.4. So you could see that you have an arrow pointing that way and an arrow pointing that way. So if you combine those arrows, they kind of point in this direction together, sort of in the upper left direction together. So there is nothing on the lower right side of this molecule to cancel those out. There is no other arrow here. So this molecule is polar. It has 2 nonpolar bonds and 2 polar bonds, but the whole molecule is polar. Now I know what you're thinking. You're thinking, yeah, but can't I draw that same molecule like this? Yes, you can draw the molecule like this, and if you draw it like this, it looks like the dipoles cancel out. But remember, this is flat paper. There is no way to get the chlorine-carbon bond on one side exactly opposite the chlorine-carbon bond on the other side when you make this molecule in 3D. Let me show you again. See, it doesn't matter where I put the chlorine. So this is the molecule as I drew it, the Lewis structure. It has the carbon in the middle, and the chlorine on top, the chlorine on the bottom, and the hydrogen on the sides. That's how I drew it. And I'm thinking that one of you will think that you should be able to cancel the dipole here with the dipole here. But this is actually 3D. So if you just turn it a little bit, this is still the same molecule. I have not done anything but turn it. You can see that these are, they cancel each other out partially, but they're still pointing to the left a little bit. There is nothing here that is pointing to the right. So no matter where you put these chlorine atoms, they are always going to be pointing a little bit towards one direction, which is not canceled by anything else pointing in the opposite direction. So this molecule is polar, right? You will see that when you make these toys.